Hello, I'm John Linz, and welcome to the Neural Network Workshop series. Today, I'm going to go over activation functions and when to use them, which activation functions are better suited for various applications. At this point, I'm assuming you've watched the previous videos where I went over neural networks in general and how they learn. Now we're going to get more into the technicalities by talking about activation functions. So, what is an activation function? So, as mentioned earlier in another video, the activation function it determines the final output of each node. So if there is, for example, a limited range, then the output of that node is restricted on that range. So just think of it as it's the deciding factor. Another thing that I should mention is that each activation function is used for different tasks. So there is not just one good overall activation function that is just the best at everything. It really depends on what you're trying to build and what you're trying to accomplish. You can see I put the equation in LaTeX up here. So as you can see, when the input is negative, it just outputs a 0, and when the input is positive, it just outputs that input. This is the binary step, which is great for classifying binary things. When the input is negative, it outputs when the input is negative, it outputs 0, and when the input is positive, it outputs 1. This is the sigmoid, and there's one interesting thing about the sigmoid that I would like to touch on. It's what's called the vanishing gradient. Is a problem actually when training neural networks that occurs very often. When the input hits a spike, so if it's very large in either the positive or negative direction, the derivative is actually very small, and you need the derivative when when you do gradient descent. When the derivative is small, there is not much progress when training the neural network. It does not learn that much. So to demonstrate this problem with the vanishing gradient, I've rendered a graph of the sigmoid activation function, as you can see here, and its derivative. And like I said, in the infinitely positive direction, as you can see, the output just gets so close, or rather the derivative, or the output of the derivative gets so close to 0 that no progress is being made during the training process. So that's a problem. There have been attempts at solutions. For example, LSTMs, which stands for long short-term memory, and then besides that, the best solution is just to go for another activation function and just ditch the sigmoid in general. So and this of course does not make the sigmoid a bad activation function. This is just a problem that occurs and you should be aware of. And then this is the hyperbolic tangent, which is of course a trigonometric function. This is the soft plus, and as you can see, like I mentioned, it is nonlinear, but all the outputs are positive, always. Okay, so I'd like to show you how the outputs of each activation function vary. As you can see here, this is sort of like a pseudo neural network in Desmos. This you can picture as the input vector. This you can imagine being the weight vector. This is computing the dot product of the two vectors to get a single numerical output, which is -1/2. And now I'm simply inputting that into all these different activation functions. And if you remember, this is the hyperbolic tangent, this is the ReLU, this is the sigmoid, the binary step, and the soft plus. And as you can see, just observing the various outputs, you might notice that since the input is negative, since it's -1/2, both the ReLU and the binary step are outputting 0. And then you can also take a look at these other outputs, which aren't 0 because they don't just collapse to 0 when the input is negative. So for the hyperbolic tangent, it's -0.68. For the sigmoid, it's 0.3775. And for the soft plus, it's 0.464. So you can really see that it really varies in the output. And in the next video, I'm going to go over the derivatives of common activation functions. So stay tuned for that. Thanks for watching.